Corrector, you're muted.
No, I think I'm not.
Yes. Very well. I think everybody's in. And I would first of all like to welcome you all to this academic ceremony. And Professor Dekker, you don't wear your beret when you're sitting down. That's officially. You only wear it when you're standing up and we are sitting down. I also would like to welcome the candidate. I think he is situated in China at the moment. I'm not sure. Yes?
Yes.
Very well. Thank you very much. So hereby I open officially this academic ceremony in which Mr. Chong Zhang will defend his academic thesis entitled AI in Medical Imaging and Novel Cancer User Support. May I invite you, Mr. Candidate, to present a summary of your studies and the conclusion of your thesis in the next 15 minutes. And I'd like to give you the word.
Yeah, sure. I hope you are able to see the screen right now.
Yes, we can see the screen.
Good afternoon, dear Prorector, members of the proposition, colleagues, friends, and family. Thank you for being here today. My name is Chong Zhang, and today I will defend my thesis titled AI in Medical Imaging and Novel Cancer User Support, which explores the topic of medical imaging, radiomics, and federated learning. Cancer cells are different from normal cells in how they grow, how they look, and what they do in the body. Even though cancer is common, there are actually many steps that a normal cell has to go through to become a cancerous cell. The most remarkable features of cancerous cells are uncontrolled growth, not responding signals from other cells, and they are neither repelled or replaced. Cancer cells reproduce rapidly before they have had the chance to mature. This continued replication often results in a tumor being formed. From last slide, we already know how tumor grows, but since they grow inside of human bodies, we need to at least find them out. Medical imaging is like taking a picture of inside of the body using special machines. These images help doctors see if there are any problems like tumors, broken bones, or other health issues. CT shows cross-sectional images of organs and tissues, and MRI shows detailed images of soft tissues like the brain and muscles. As you can see in the right picture, a low-grade cerebellar tumor is only faintly visible on CT, but only if you know where to look based on the MRI results. AI refers to technology that can learn, think, and make decisions like a human, but faster and more accurately. In healthcare, AI can help doctors by analyzing medical images, finding patterns, and predicting patient outcomes. AI looks at thousands of medical images to learn what healthy tissues and cancer cells look like. It then helps doctors by pointing out suspicious areas in new images, helping them make better, faster decisions. In previous slides, I have introduced how AI can segment tumor automatically. In this section, I will introduce how radiomics could handle the segmented tumor and turns it into information. Radiomics is the science of extracting detailed information from medical images like CT scans or MRIs. It involves turning complex images into a set of numbers that describe the tumor's shape, texture, and other features. These numbers can reveal hidden patterns that are important for diagnosing and predicting how cancer will behave. By analyzing these features, doctors can better understand how the tumor is likely to grow, and respond to treatment. In chapter 3 of my thesis, we developed a radio mix model to predict clinical lymph node staging and combine it with clinical model. The clinical model contains age, tumor location, radiological staging, and tumor regression grade. The combined model showed better performance in both training and validation cohort, as you can see in the graph. AUC is a performance measuring metric for prediction models. A value of 0.5 means the model is randomly predicting, and the value of 1 means a perfect model. The experiment indicates that radiomics can help with clinical lymph node staging and assist doctors with a better treatment decision. However, since the conclusion we found in chapter 2 that a discriminative index of 0.7 is likely to be the current status of performance of radiomics in immunotherapy studies, plus the fact that ensuring data quality and diversity should be prioritized over the complexity of algorithms, we continued researches to find solutions. An important source of long reproducibility or limited generalizability in radiomics that demands more attention is image noise. This noise decreases the image texture, as you can see in the left graph. Zoomed eyes get blurred when noise in image increases. In this experiment, we deployed 2 deep learning generative models for CT images denoising, and both of them achieved good performance, hence increased the reproducibility of radiomics features, as you can see in the right graph. In centralized learning, patient data from multiple hospitals is sent to a central server to train machine learning models. The approach works well for creating strong models, but it raises serious concerns about data privacy and security. Patient data must be stored and shared, which can be risky and costly, especially under strict regulations like GDPR. Uh, So there's some error here. Now we'll continue. Federated learning allows multiple hospitals to collaboratively train a machine learning model without sharing sensitive patient data. Instead of sending raw patient data to a central server, each hospital keeps the data locally and only shares model updates or parameters, which ensures data privacy. This method complies with GDPR regulations by protecting patient data and ensuring it never leaves hospitals' premises. In this case, federated learning encourages more institutions to join the model building and hence increase the data diversity at the beginning. Overall, my research has made substantial contributions to advancing the field of radiomics and its practical application in medical imaging analysis. In the systematic review of Chapter 2, I identified critical methodological gaps in current radiomics studies for immunotherapy response prediction, establishing important quality benchmarks for future research. I then demonstrated the practical application of these principles by developing a robust, combined clinical and radiomics model for lymph node staging, achieving stable performance in external validation. My pooling-based feature selection method has provided researchers and healthcare professionals with a standardized approach to feature selection, enhancing the reproducibility and reliability of rhythmic studies. Additionally, I addressed the two crucial challenges in medical imaging: image quality optimization through deep learning-based denoising techniques for low-dose CT, and data privacy concerns through the implementation of federated learning approaches. For the future, I would like to investigate more on federated learning and advanced deep learning methods like transformers. Recent studies have shown that federated learning performs well, coping with multiple hospitals. In my previous study, I focused mainly on proof of feasibility of the personal health training infrastructure, but did not perform a deeper investigation on complexity. Hence, experimenting with more complex deep learning models and adding more client nodes would be a possible orientation of future work. Second, transformers, originally designed for natural language processing tasks, have gained popularity in the imaging field. Compared to the CNNs, transformers have the following advantages: attention mechanisms, flexibility in input image sites, integration with attention maps, and multimodalities. This has led to the emergence of the segment anything trend, which is a rising star in the medical field. Transformers models are expected to be the next frontier for AI in radiation oncology and medical imaging. Finally, thank you for your attention.
Thank you very much, Mr. Candidate, for your presentation. Well in time, well illustrated, and I think we are all ready for now to discuss this with you. And since this is an online thesis defense, I would like to mention that there are quite a lot of people, maybe also from your colleagues in China. This is a live event, so everybody can look also in China to this deliberation.
Yes,
We
indeed.
have, for your information, we have 5 opponents, so there will be 5 opponents who are going to address questions to you. And I would like to give the first word to a member of your assessment committee, Professor Van Ooyen, who is an expert in AI in radiotherapy of the University of Groningen. And I would like to welcome also that he joins online, and I'd like to give him the word. Professor Van Ooyen.
Thank you very much, Mr. Prorector. Dear candidate, first of all, congratulations with your thesis. I read it with interest. Very nice collection of chapters, and also I would like to extend that congratulations, of course, to your supervising team. And then I would like to discuss some of the topics that you cover. And to start with, I want to go to chapter 2, where you did the systematic review of the radiomic biomarkers. There you state that basically the methodological robustness of the studies that were examined, that were available now, varied greatly, and that there were shortcomings in, for example, feature selection and dimensionality reduction that was done in those studies. Given the impact of these steps on the model performance that you see in your review, which specific AI techniques or methods do you think would be most suitable to address these shortcomings and develop more robust models for predicting the response to immunotherapy?
Esteemed opponent, thank you for your question and your compliment. So in chapter 2, I systematically reviewed all the studies that do the radiomics immunotherapy response prediction. And I find that actually most of them did not kind of meet the criteria that we made for the benchmark. But if you ask me what part is the most important and also would advance the future study, I would say start from the beginning to have the data acquisition step more standardized. When you have the best of the data you have, then actually in my scenario, I think even the most basic machine learning model or deep learning models could have very good performance. I hope that answers your question.
Yeah, so that's a very interesting thought. So you say, okay, you have to start at the beginning, getting standardization in the basically on the acquisition side already.
Yeah.
How could we get there? Because that's of course quite a challenge because up until now that was not the case, especially when you look at medical imaging in MR, for example, then there's a very wide variability in the way people acquire their data, but also in CT. So how are we going to get there then? Do you have any idea?
Highly esteemed opponent, thank you for your question. That's really kind of like going to be still an open question, and it's still going to be an open question, I have to say, for many years later. So having this data more standardized is coming to be a very hot topic actually. So for example, for the transformers new paper that they have this kind of segment anything. So actually they do not use any new techniques, but they have a very good way of the data preparing. So they kind of build a data storage and they made the data to produce data using AI, so they can have like more data. So that's kind of one direction. So have the data numbers, but for data quality, still we have to kind of, so the society and the whole world has to work together to have like more standardized regulations or the way of building the images or clinical data. So that's the way I think how we can have better images or data at the beginning.
So you wouldn't see a role of transformers, etc., to maybe do a kind of pre-processing before you go into the radiomic step of the data that was acquired. So you don't need to do that whole standardization of the acquisition, but you transform the data into something that is more generic. Would that be something that would be feasible, do you think, or do you still want to rely on the acquisition to be changed?
Actually, there was another very interesting paper that, so even after the very hot topic of transformers, so they kind of borrowed the idea of transformer, but they bring it back to very traditional convolutional neural networks, and still, and even surprisingly, it achieved better performance than transformers. So I have to say that I still put the image acquisition and image pre-processing as the very first and the most important part.
Okay, very good. Now, in the same in the review, you also emphasized that none of the students basically examined the clinical usability or cost benefit of using radiomics in this use case. And that's apparently something that is very much lacking then in all the literature there. So probably it's very difficult for people to do that because they don't do it. So do you have any idea how that should be done, and how people could um, perform those kind of evaluations to a level that you can, yeah, more easily introduce things into clinical practice?
Highly esteemed opponents, thank you for your question. I think that's a very interesting one. So normally for researchers, when having an experiment or having to start designs, I think most of them were doing it alone without the doctors or clinicians. So I would suggest that we, at the beginning, start the experiment design or the study design along with doctors and clinicians, that they can have a better doctor side view of how that, okay, so what is the end of my experiment? Should I end with a model only? Or should I end with having this model more sufficiently deployed in the daily clinical base? So in that part, I think then we can have a better output.
Yeah, that's an interesting thought. So you
And
think that that part of it is because of the lack of collaboration between the clinical and the technical people. That's
yes,
one
indeed.
of the ways to solve this this issue. Um, are there also technical ways of moving towards a better implementation? So could you
Technically,
how would you
that's a fun one.
so how would you do a
I
clinical usability analysis, for example?
For doing a clinical usability example, I think still we cannot do it only with researchers with AI or deep learning basic background. So we still have to collaborate more with the doctors and having. So we need to know exactly that in which step or in which process of the daily clinical decision that the model can actually help the doctors. We know that, then we can have the model and then give it directly to that step and then make that decision. So yeah, that's my answer for it.
Okay, thank you. I'll leave the rest of this discussion to the more clinical people in the opposition. So I want to go also to chapter 3 with you, where you describe an attempt to validate a radiomics model for predicting lymph node metastasis. And you do external validation and see that you cannot replicate the results fully in that external validation. Now, most of the times that can be because of the technique of scanning, but it can also be because of difference in the patient population. So how do you cope with those differences in patient population and treatment protocols between the development and the validation cohorts? And how could you approach to it to improve that generalizability of your implementation?
Thank you for the question. So that has been always kind of a trade-off between the model's strong ability and the model generalizability. So in the later part of my experiment or research, I have kind of researched on how to extend this generalizability by using federated learning, because it's at the beginning kind of adding more hospitals, including people from Asia or from Europe, from the USA. They have different regions. Then we have the more direction of the data at the beginning. So in that way that we can solve this model generalizability. And for feature selection part, and so in chapter 4, actually, I just go deeper and trying to find a more standardized and way to do this feature selection that kind of keep the feature that represent most patterns and having the most robustly and generalizability. So I think, yeah, in 2 ways.
I have to interrupt here, so I think officially the time is over and we have 4 more opponents to go, and therefore I would like to change swiftly to Professor Bates-Tan. Bates-Tan is professor in radiology at the NKI Center in Amsterdam and also affiliated with Maastricht, and I would like her the opportunity to discuss with you. Professor Bates-Tan.
Thank you very much, Mr. Prorector. Dear candidates, I hope you hear me well. Congratulations with this very important work. I think that AI for clinical use is something that we really need to investigate. So congratulations, and also your supervising team. I would like to delve deeper into this chapter 3, your use case, and the use case of lymph node in esophageal cancer. So the results with the PET model are very disappointing. That is especially in the validation. So in fact, no conclusion yet can be drawn that it is ready for clinical use, right? I'm correct in that, right?
Yes, you're correct.
Okay, now my question is this. You are always referring to standardization and acquisition of parameters, but would if you only look at the CT component of the PET, what do you think? How would it influence your results? Because the CT part, seemed to be more standardized, especially as a radiologist. I know that the CT, I mean, worldwide we have a protocol that is similar in CT, and there's hardly any discussion in contrast to MR. So have you thought of that, or why did you not specifically focus on that?
Highly esteemed opponent, thank you for your question. So I have to say at the very beginning, so we only have the CT and PET-CT images, but we do not have the MR images. So that part was kind of excluded at the beginning. And for the very kind of disappointing results, I have to say, but actually the way that we look at this result, it was kind of so we find that actually the radiomics features we extracted from the CT images kind of can have some adding values comparing to the clinical features only. So that's kind of the happy findings that we got from the results.
So if I understand well, you looked at the CT only images also. You modeled also the CT only, or is it the entire PET CT? Can you tell me that a little bit more? Because it's now, I'm a bit confused.
Thank you for your question. So in this part, we look at CT and PET-CT. So it's two types of the images that we have.
And so is there any difference? Was there a benefit for the CT model? Did it perform the CT?
So actually, we do find that the CT images model actually can achieve the best performance in the training cohort, and I think that part you can also find in figure 3.
Now, the next question is this. I saw a difference in your inclusion. The patient cohort were different. The development, for example, in tables, you showed that the development cohort, there were 20 who had a neoadjuvant chemoradiotherapy, and in the validation cohort, it was 60. So there is quite a difference. Don't you think that would also result in a poorer performance of your model?
Yes, I would have to say that might have been a very major result and explanation for the very poor external validation results for the patient distribution. So yeah, you're correct.
Okay, so how because can you tell me exactly how you modeled it? You modeled from the primary tumor to predict the lymph nodes, right? How
Yes.
did you do that with the ones who did not immediately go surgery but had the neoadjuvant treatment, either chemo or chemoradiotherapy? How did you model that? Was it on the baseline and post neoadjuvant treatment, or how did you do that? What is the methodology that you exactly use?
Thank you for your question. So if I get it correctly, you are asking about the image acquisition part, right?
Baseline. So you extracted the features from the primary tumor if the patient would immediately go to surgery. So what did you do with the patients who had first the neoadjuvant chemo or neoadjuvant chemoradiotherapy? How did you handle the methodology? Which image timeline did you use?
I have to say that for that detailed part, I cannot record it very detailedly. But I think for inclusion criteria is that we only include the RIs and under the chemotherapy. So, but I don't remember that detail very exactly. I'm sorry about that.
No, that's okay. The reason I ask is because in esophageal cancer, we are going into an area that we are not going for surgery anymore. And it would be, and the nodes are the main issue. So if you would work on AI, if you have a model that can predict the nodes after they have been treated and the tumor has so much regressed that the patient does not need surgery anymore, the main question is not the tumor, but what happened with the node around. And that is a model that would be very interesting. So that was why I asked this question. But anyway, I'm okay with your answer. I want to go a little bit more into this a general question, because you said very easy, like, okay, acquisition is a parameters, we should do that. And societies should work on that. Now, sorry.
Can you please make it a short question, because you're running late?
Okay. So then I only would like to ask the question, what you would advise to us radiologists or to clinicians. But maybe you should only focus on the radiologists. What should we do as radiologists?
So actually, my background was more in machine learning and AI. So as that role, I would kind of ask more from the radiologist about having the images marked more clearly, and yeah, that's kind of more what I wanted actually. So kind of explain the images to me more clearly, and then I kind of totally understand which part I'm going to look at and what kind of the model results I'm going to reflect into the clinical databases.
Okay.
Thank you. I think we have to close this discussion and move swiftly to the next opponent, which will be Professor Hurkmans. He is head of the Department of Radiation Therapy and Clinical Physics at Eindhoven University, University of Technology, and I would like to thank him that he joins and would like to give him the word.
Yes, thank you very much. And I would first want to congratulate you with this thesis, and obviously also your promoter, co-promoters, and colleagues, and your family and friends as well, because I think it mostly is a lot of work of yourself, obviously, but also the people surrounding you. And I like to take this opportunity to deliberate with you on mainly chapter 6 concerning the federated learning. I think that's a very interesting topic, and well, you also mentioned that in your presentation might be something to look for more in the future as well. And you had a very nice example on how you could do this concerning ICT problems, but also presented a use case. And for that use case, I wanted to go in a little bit more detail. And the first question there would be around figure 4, which can be found on page 108. You depicted training loss there, but it seems like the skills might be interchanged, or at least I'm confused. I think the X and Y axis should be the other way around, or am I misinterpreting this figure?
I think I made a mistake. So actually, the X should be the epoch, and the Y should be loss.
Okay, then that's fine. That can happen. And here you see the loss of the different nodes, which is very interesting to see how a separate node converges. It tells you a lot about the data, and if you're overtraining one of the nodes, for example. And you have a curve which I think is the centralized learning curve. But I do miss the average curve there as well.
So the average curve means that for the federated learning, and we are having this weighted loss. So we kind of average the loss between the node 1 and node 2, and then have this average loss. This one is going to be compared with the centralized learning. And if they are very similar or having very similar performance, then we can say that this federated learning architecture works. So that's kind of the purpose of this graph and experiment.
Yes, but am I correct that there should be 4 curves in this graph? I see 3.
That's because the dashed line of that average was totally overlapping with the decentralized learning. So maybe you sorry that maybe you think it's 3 lines, but it's actually 4, but they're totally overlapped.
They're totally overlapping. Now you point me to that. I can see, but that was very difficult to see. But it might be I'm a little colorblind for this type of images.
But I'm sorry for that, but actually there are 4 lines.
Yeah, okay. Thank you very much. That explains a lot. And then you explained quite well that you try to leverage the federated learning to correct for different sizes of the data set, which I think is a very important step. And you describe quite nicely that this is a weight balance based on the number of patients or data sets per node. And I was wondering if you have maybe simulated nodes that are quite different from each other, because here you have probably some data which is not that different. And could you maybe speculate what would happen if in one node, for example, you would have data from very small tumors, and in another node you would only have data from very large tumors? How would that converge in your model? How would that affect your weights and your model?
There is highly similar opponents. Thank you for your question. Actually, that's kind of the source that I have after my experiment, because for this experiment it was kind of only a proof of feasibility experiment to see whether this personal health train works well and how we should build the federated learning models from scratch. But in that very extreme cases, I have to say, if one has really real patient data and one have really big patient data, so my algorithm should works good because it kind of balance the number of the patients, but still there are some really recent papers that kind of are experimenting on how we should deal with this different size with different sizes. But also that part, I think the most important part is not for conversion. It's more about like a mathematical or technical problem, because when we have like more centers or more hospitals, then there might be one situation that one of or two of the hospitals just went down, maybe because of the internet or communication errors. Then what we should do? I think that is kind of the more tricky and extra problems to look at.
And do you understand that you think this is a problem during training, when you're actually training with that data set, or also afterwards when you have developed the model completely or trained it completely?
Yes, I have to say that if every node communicates well with the central server, then ideally they should be able to reach the same convergences or the same losses comparing to the centralized learning. So actually now the more solutions we are trying to find is to figure out what should we do when one of these nodes went down, and what should we do? Should we stop it for now for one iteration, or should we wait for 10 iteration, or we should directly drop this node and whatever, and trying to find the most similar performance for comparing to the centralized learning. Yeah.
Okay. And I noticed that in some of the data you have, there is actually no Dutch data. Is that correct? And is there a reason why you could not access the Dutch data? Is there a law prohibiting that or something else?
I think that's so the starting point of this study was kind of starting from a CRISPR challenge part, and we want to start it very fast to prove the feasibility of our infrastructure. So we just simply started with some open source data. So it's not the business of the regulations or anything to do with the Dutch data. But ideally, in the future, if I have any chance to do that, I would like to collaborate with Chinese and Dutch data and see what we can find. But that's kind of in the future, I have to say.
Yeah. Well, that's one of the reasons why I'm asking, because I think this is indeed very interesting material, and I hope we can open more nodes and obviously also in the Netherlands. Would be a nice collaboration in the future, maybe.
Yeah.
Thank you very much. And then we have to proceed to the next opponent, which will be Dr. van Soest. Dr. van Soest is involved in the Brightlet Campus Institute for Smart Society. And I would also like to give him the opportunity to discuss with you, Professor Dr. van Soest. I give you the word.
Thank you, dear Prorector. Dear candidate, first of all, congratulations on this thesis, on this very nice work. Not only you, but also your supervisory team. And I find it very interesting to read, but still have some questions I want to ask you on this one. And I want to start with the title, actually, and especially the second part of the title, which talks about user support, the actual last two words. Can you maybe elaborate what do you mean with the user in this context?
Actually, in user is a very general word. It can be like the society, the hospital, the researchers. So actually, in my thesis, the users in terms of more for the researchers and the doctors. Yeah. So in my thesis, actually, I do give a lot of suggestions for researchers and doctors that do not understand much of the AI or the feature selection part, but they can kind of start from scratch to have this kind of very basic or very general baseline of the whole radiomic study baseline to follow, and then have their study and have their very basic results. So that's kind of explain your question, I think.
Yeah, so it's not only the outcome where you say is relevant, but also the procedures, the methods that you've used, right? Which are sometimes where you tried new and novel things. Okay, then I want to move to chapter 3 and specifically table 2 in chapter 3. And that links, if I'm correct, with proposition number 2, where you talk about a model which has good discrimination. And I want to would like to know from you, what do you think about that good discrimination? Does that fall together, or is it similar to a good model? Because in the paper itself, or in the chapter itself, you mostly refer to the AUC in comparison to the other metrics. So I was wondering how would you place those metrics into and how to evaluate them in terms of what are now good metrics to use, and why an AUC is more important maybe than others.
Highly esteemed opponents, thank you for your question. So that's kind of a very, I have to say, it's a question that you should ask yourself at the very beginning. That's also what I talked before. So it kind of has to go back to the very beginning. So when you have some doctors with you and you can discuss, so you do have to ask yourself or ask your colleagues that what kind of metric I should be looking at. So, for example, a patient went to go to the hospital. He wants to know that whether he has cancer. So it's okay that we say that he does not have cancer, but he doesn't have a cancer, but we say he has a cancer. So it's fine that he can do a second check. But if he does have a cancer, but we say no, then he might just miss that chance and then just miss the whole chance for the treatment. So we cannot accept that. So in this case, we might have to look very exactly at the sensitivity. But AUC is kind of like a more general way to look at the model. So it's kind of like a compilation of all the other accuracy, sensitivity, specificity stuff. So most of the time we just look at AUC, but for some specific domains, we have to look at some other specific metric that depends on your experiment design or your goal, I have to say.
Right. Yes. All right. Then I want to move a little bit to chapter 4 in there as well, because there is also talked about AUC, among others. And there I was wondering, because in chapter 4 you apply a new method for feature pooling and signature development and pooling. How can we make sure that this new method works better than current methods available?
Actually, in this part, we are not going to introduce or kind of compare this method with the state-of-art method or algorithms. We're trying to kind of build a very baseline approach for the whole process. And then we were trying to say that actually the goal is not to achieve the best result, it's actually to maintain the robustness at the very beginning. So actually, if you look at figure 1 of this kind of with this workflow of the proposed feature pooling method, you can see that actually every step every little step we choose was kind of very, so we're not choosing very dangerous or very outgoing process that can achieve the best result. We're trying to find a way that's kind of most stable and has maybe kind of trying to make the features we select as the most generalizability and robustness.
Right. And how do we know that this robustness is then better than the current methods out there?
So
do we know that in terms of?
I think if I talk with you before the experiment, I would have adding some other more experiment for having maybe a benchmark or something that might be able to enhance my results more. But yeah, for this certain past studies, I have to say that I did not do that, and actually the purpose was really simple, is that you give some doctors that has very few technical experiments or feature selection experiments to start from scratch very easily. Yeah.
Right. Yes. Then I still want to move quickly to chapter 6, to the federated learning chapter. And the first question there.
There's time for one question, a short question.
One question, yes. How would you handle here privacy versus what you're referring to in your thesis throughout the work in terms of data heterogeneity? Can you detect still data heterogeneity in a federated learning setting without having access to the data?
So actually in my discussion part, I already talked about how that we can make sure the security and privacy was done. So some secure communication that you can at the start to encrypt data transmission between clients. And then you can also kind of anonymize the local updates before it's sent back to the central server. So and etc. So in this way that we can have more data at the beginning, and also we can protect the privacy and the regulations and the leakage of the data.
Okay, thank you
Thank
very
you.
much.
Thank you very much. And we will proceed to the last opponent, which is Dr. Feiten. She is affiliated with the Department of Radiology at our university. And I also like to give her the opportunity to discuss with you. Dr. Feiten.
The Department of Radiotherapy, but I don't think it
Sorry.
matters. Dear candidates, congratulations on finishing your thesis. Also, congratulations to your promotion team. I would like to start with a more higher level question, which is related to statement 1 or the proposition 1. Should I read it, or we don't have paronyms here, right? Who's going to read it?
I think you should. No, let's the candidate read it.
Okay.
The candidate itself.
So proposition number 1, a discriminative index in the vicinity of 0.7 is likely to be the current status of performance of radiomics immunotherapy studies. Yes. Yeah.
Yes, so that kind of triggered me when I was reading it, because what I think, at least, is that radiomics has been criticized a lot in the last few years, right? Especially for its heterogeneity, for example. In my opinion, that sort of limits fundamentally the clinical application or applicability of radiomics. And in chapter 2 and in this proposition, you basically say, okay, for at least immunotherapy, the discriminative index is likely to be no more than 0.7. In my opinion, that's pretty generalizable, right? It's not just immunotherapy, it's probably radiomics wide. So given those views, I guess, can you tell me whether you think radiomics is still usable clinically, or should we move to something else that we could use, to actually improve the clinical care in some way?
Highly esteemed opponents, thank you for your question and compliment. Actually, that's the question I have been thinking around for the whole of my PhD study, because actually I have to say that most of my radiomics studies and results did not. Sometimes it performs really good in the training in the training set, but it did not actually perform well in the validation part. And I have to say it also follows my findings in chapter 2. The 0.7 is kind of actually the gap over there, but still doctors are still very suspicious for the new deep learning method, because it's still a very, very black box. But still, although there are also some visualization way that, like the activation map, you can see what the models was looking at, but it was still very vague. For doctors, if there is a very kind of very stable model that I maybe say 0.75 AUC, it still can be explained to doctors that which features or which, for example, the shape of the tumors that he should be looking at, and then give some adding values to the doctor itself to think about it. And also for some clinical uses, such as the nomogram, it's the radiomics study still be very useful. So I think in the future it won't fade, but maybe one day the deep learning part can reach a really, really high AUC, for example, 0.99, then I think maybe we don't care whether it's a black box or not, then we just use it. So I think for now, radiomics is still very useful.
right? So basically you're saying, yes, it's not that great, but it's at least explainable versus deep learning methodologies. Do you, however, see any changes that could be used in radiomics to make it more robust? Or do you really think this is the limit that it can reach? And we just have to, be happy with the fact that it can reach 0.7?
I think maybe at least we can try to combine the new technology and the radiomics, for example, the deep learning features and the radiomics features, and kind of trying to find a correlation or relation between them, and trying to maybe just expand the current radiomics calculation, because now the radiomics calculations is basically handcrafted by some mathematical formulas. Maybe we just we haven't find some other more complex patterns or complex algorithms to calculate the radiomics. If we can someday expand it, and then maybe then the radiomics can be really powerful.
Okay, that seems like a good avenue to investigate, definitely. So that actually leads very well into my next question, which was about chapter 5, where I wanted to ask you. So in chapter 5, you did a combination, right, of deep learning and radiomics. You used deep learning for the denoising, and then radiomics to extract the features. I would really very much like you to explain to me why you decided on this methodology versus an end-to-end deep learning methodology, which is, at least nowadays, quite common, right? You input a medical image, even though it's a black box, and the prediction rolls out, and it takes care of denoising and all those steps within this end-to-end product, which would reduce the number of steps we need to take. I'm curious to hear why you decided not to use that approach, but still keep radiomics in your methodology.
Thank you for your question. Actually, so for the end-to-end pipeline, actually for now, deep learning was really dominates in some certain parts, such as like the tumor segmentation. Deep learning has doing really, really well, and I think most of the hospital has been using that. And also for the denoising. So this kind of GAN neural network and the new deep learning networks can do really, really good for I'm doing that in a bottleneck layer, and then, but for kind of more traditional prediction and prediction tasks, I think this goes back to your last question. For the last prediction, we still want it to be explainable, because that part is really going to influence your final treatment decision. So the doctors or even the patient wants I want to know why you lead me to the decision, so I can be kind of more comfortable with that. So that's kind of the reason that I do not use end-to-end pipeline for this certain study.
Okay, thank you. I still have 1 minute, right? So I can ask one final question, perhaps. For chapter 6, then I'll keep it quick. I'll make it quick. You present federated learning, right, as a solution for privacy concerns. However, there are many challenges related to federated learning, right? Heterogeneity of data, standardization, etc. Given these barriers, do you think federated learning does have a use case for use in clinical care or healthcare in general in sharing data, or do you think it will very much be will stay a research methodology?
I do agree that federated learning should be really useful, because actually these challenges I have to say, it's really, really.
Hora asked,
Dear Mr. Candidate, you have now a choice. You can finish your answer, you're allowed to do that, but you also can say, I leave with it, and then we stop. It's your choice.
I live with it, and we can talk about it later.
Okay, you live with it, you don't answer further. Very well. Then, Mr. Candidate, the time officially appointed to defend your thesis has now officially passed. The degree committee will now sit together, and we're going to another room, and we're going to discuss not so much the quality of your thesis, that has already been approved, but we're going to discuss the way you have defended your thesis this afternoon. And I request to wait for our deliberation and to the return that we get together here in this online session again. Thank you.
Thank you.
And yes, she is moved to the other room perfectly. So we can proceed. And the candidate is already waiting. I still call him the candidates. So Mr. Zhang, Mr. Chong Zhang, the degree committee here present, online, of course, has assessed not so much the quality of your thesis, but much more the way you have defended your thesis this afternoon. And in view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you officially the degree of doctor. Professor Dekker is authorized to confer upon you this academic distinction in accordance with Dutch university custom. And therefore, I invite your supervisor now to stand up, put his beret on his head, and I would like to give him the floor. Professor Dekker.
Thank you, Mr. Prorector. But before I do this, I will need you to promise something. So, dear candidates, do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
I promise.
Then, by the authority vested in us by law, and in conformity with the decision of the committee here present online, I hereby confer upon you, Chong Zhang, the degree of doctor, and grant you all rights attached by custom and law. As evidence of this, you will soon receive the degree certificate signed by the rector, the secretary, and the supervisor, affixed with the official seal of the university, now shown to you by the beadle.
Thanks.
Thank you.
Thank you all.
Please unmute if you use this here.
See us clapping. Yeah, thank you. I now give the word to one of your co-supervisors, Dr. Lobo Gomez, for the laudatio.
Dear Chong, you did it. You have shown incredible perseverance in achieving this great milestone. Let's recap the journey that brought you here today. You joined the Clinical Data Science group in 2018 to do your master's. At this time, the group was called Knowledge Engineering, much smaller, and everyone was sitting at Maastricht. You wrote your master thesis on radiomics under daily supervision of Shen Wei, who came to become a close friend to you. Due to your great success with the work you did during your master's, you were offered a PhD position in the group, which you started in 2019. 1 year later, you joined the Amicus project, which provided your funding for the remaining 3 years. In the meantime, Shen Wei went back to China, and you got Karen and Inigo added to your supervision team. Your work in Amicus was focused on data verification and federated deep learning, and the position was given to you because of the success you had in previous experiments with federated deep learning using PPGLI, which is now Vantage 6. You should be really proud of probably being one of the first people that run federated deep learning experiments using medical imaging. The Amicus project started, though, during a difficult period, the corona pandemic. You had to adapt with working from home with much less supervision than you were accustomed to. This was a difficult experience, but you found your way around it. 1 year after the Amicus project started, I joined the group and had the pleasure of having you as my first PhD student. I remember you saying a couple of times that your research passion was radiomics, and indeed, 4 of your research papers were radiomics related. Anyways, it is very nice to see some years later that you are getting excited about using transformers to learn prediction models with medical images. You are also convinced that federated learning will solve all data sharing issues, and you should be very proud that you gave some contribution to this field. There were some rough moments in your journey too, when André, Inigo, and I were not sure what we could do to support you. Moving to a different country with a different culture and language to pursue a PhD, which is not an easy thing, is not a simple undertaking. There are 8,000 kilometers between Wuhan and Maastricht. The physical distance from your family, your girlfriend, your closest friends sometimes took a toll on you. Finding the motivation to complete the task you set yourself to do was sometimes a bit difficult. However, you displayed great resilience by never giving up, and for this, we are really proud of you. You had to go back to China in May 2023, and we decided that you could finish your thesis at your own pace from there. It was with great happiness that in January 31st, 2024, we got the first draft of your thesis. Now, 1 year later, we have the pleasure to see you achieving this great honor. There are also some funny things about you. You moved flats a couple of times. Sometimes we thought that you were moving flats every 3 months or so. You also had your laptop crashing many times, and of course, in the most inconvenient moments. We can explain it with Murphy's Law. Anything that can go wrong will go wrong. During your years in the Netherlands, you also did take the time to discover Europe and took trips every time you could, some with members of your family that came to visit you. This curiosity about other places and other cultures was also something we observed in your work. You also always had a big smile when you came to the office. You are very communicative and easygoing and had a good relationship with all our work colleagues. Some of your funky shirts and your caps were also a bit of a trademark, and I could often spot you even without my glasses. As I said before, you were also my first PhD student, and I learned a lot from you. For this, I would like to thank you. In your progress meetings, besides talking about work, we also talked about life and found out some common interests, like being raised with Japanese culture influence, reading mangas, and watching animes. Chong, we wish you all the very best on your new job and a very successful future. Gong Si Su Ni Wei Lai Yi Che Chung Li.
Thank you.
Congratulations.
Congratulations.
Thank you all.
So, Dr. Zhang, I like to call you now officially Dr. Zhang. How does that feel? Feels good?
Good, finally. This stone
Finally.
just fell down.
That's a good wording to speak about finally, because I understand from the laudatio that it took you a year to finish it, and you returned to China in 2023. So it's a long time already passed. So you finally can proceed. And I know from the many Chinese students I had myself that once you have your PhD, the career is going much easier in China. They're waiting for this official diploma. So congratulations also on behalf of Maastricht University, also on behalf of all our board of directors, and we wish you a lot of success in your further career in China. In my congratulations is of course also your promotion team who guided you over the last years. And I also would like to thank the members of the Corona who already were expressed by Professor Dekkers. They had to cover their 9 minutes, but it takes more than 9 minutes to prepare questions for these Corona, and I would like to thank them that they joined us over here. We're going to make, or it has already been done, I'm not quite sure, to make an online screenshot. Beer, has that happened already?
I think I need to ask the technical support. Anyway, did you manage to take a picture of the screen? Thank you.
Anybody?
Yes, I did.
It's already happened?
Yes.
Yes? Okay, very good.
Very surprised.
Then I think we can proceed, and I would say again, thank you for all. And by that, I'm going to officially close the ceremony, but I give the opportunity to the members of the Corona, if they want, of course, to say a few words to the new young doctor officially. And I would like to basically, I would like just follow it here. We had already the members of the